Hello, today is January 19th and we have a lot of stuff to cover. So this is me and this is David Blackwell. So NVIDIA announced their new architecture with the character B, like B100. And this is named after David Blackwell, who was a statistician for many years, for more than 30 years. He was at Berkeley. He was actually chair of the statistics department. He is very well known, and yeah, so NVIDIA is honoring his memory by naming this new architecture after him. So these are some NVIDIA architectures, and you see there's Ampere, and then there is Ada Lovelace, who was a mathematician, many in like 1850s. And then, of course, Hopper, Grace Hopper, the famous computer scientist who coined the word bug, who created the first linker, who created COBOL language for mainframes. Who is not muted? Please mute yourself. Anyway, this B architecture, Blackwell architecture, supposed to be twice faster in inference than current record with the Hopper architecture. And then we go into transformers and into large language models. So large language models are actually very simple. And it is a multi-layer model following the decoder part of the standard transformer architecture. I will explain it in detail later. It accepts a sequence of tokens. So this is sequence of tokens, converts them into sequence of embedding vectors. So these are vectors. So each token is converted into a vector. Transform them over multiple decoder layers. So as these vectors go through these layers, input is set of vectors and output is the set of the vectors of the same number and same size, and it goes through these layers, which may be 30, maybe 50, maybe 100 of these layers. At the end, we have the same set of vectors, although they are modified, and then there is a certain part here which maps it to vocabulary of tokens and select the best token, and this token is added to the end of this input sequence. So the sequence grows. So it generates one token at a time and goes in circle. So each layer consists of two parts, self-attention and feed-forward. And again, we cover how they work later, but so each of those layers consists of two parts. First, self-attention, then feed-forward part. Self-attention contains multiple matrices, and there are a lot of linear algebra operations and softmax, whereas feed-forward layer is kind of a standard. You have one intermediate layer, which is bigger than the size of this layer, and then it goes back returning to the dimensionality of the model. So we'll cover it in more details. But first I want to mention this famous article, Attention is All You Need, by Google in 2017. So this is archive reference, and this is the picture from this article, which I hate, but everybody cites it. So you see that so they created this model for Google Translate, and it consists of encoder and then decoder. So for example, this diagram may be a little bit better. So it shows the input in one language. I think it is French, je suis étudiant, and then it converts it into English. I am a student, right? So first it goes through multiple layers of encoder, and then it goes through multiple layers of decoder, and at the end it gives this response. And by the way, it is generated one token at a time. So it generates the token, then it goes to the input of this first decoder, and so it works like a large language model. That's why people say that large language model is basically the decoder piece of the standard transformer. Okay. Next, I want to go a little bit through history. This is a very good video by La Vivienne about the history of Google Translate. And at some point, they were statistically based machines. Then they start using deep learning. And in 2016, they had this record-breaking model which used recurrent neural networks, LSTMs, long short-term memory networks, as encoder and decoder. And in the middle, they had attention block. And this was state of the art. But then next year in 17, when they published this paper, attention is all you need, instead of using attention block between those encoder and decoder, they actually included attention in both of these, in every layer of these two parts of encoder and decoder. And this is the famous transformer model. And then what happened, they started playing with combinations of using LSTMs and transformer. And for example, in 2020, the best model was a hybrid approach. It used transformer and LSTMs. But by now, LSTMs were gradually removed from all the translators, and nowadays it's almost completely transformer model, like large language model, whatever. It's all transformer based. Anyway, next, I want to talk about Mixtral, which is a modern open source model from French company Mistral. And both Mistral and Mixtral, they're similar. The only difference is that Mixtral has mixture of experts part, but we'll cover it. So first, we have some tokens in the input, then they are converted into embedding vectors. And by the way, this is done, how they embed it, they don't use like external pre-trained embedding model. They actually train it as part of training the whole model. So they convert into vectors. Then it goes through these multiple layers. There are 32 layers. And then at the end, there is a part where the output of the last layer is converted to the next token. This token is added to this sequence, and then it repeats, and that's how it generates the output, right? So we have 32 layers. Each layer, if you look closely for Mistral, it consists of attention part and feed-forward part. But in Mixtral, they take two of those layers. So they have this bigger piece, which consists of attention, feed forward, attention, feed forward. And the first feed forward actually is a mixture of experts. So you have 8 networks which sit in parallel, and you have a gating mechanism in front of them. And each token in the sequence, so you have the sequence of tokens. So each token in the sequence, this gating mechanism decide to which of those experts to route them. And it selects 2 out of 8 and routes to those experts. And the next token may go to some other experts. Now, after a particular token goes to 2 experts, they process it. At the end, they have vectors, and then they combine them together. And then it goes through other layers. So these big combined layers, there are only 16 of them. In the original Mistral, there were 32, but here we have 16. You see this n divided by 2. Okay. Mixtral, how it works. So this is same thing I just wrote. So Mixtral of experts, this is their paper, which is on arXiv. And you see there are 26 authors. This is basically the whole company, Mistral, which is in France, Paris. And you can read this article, and it goes through all the details and provides statistics. I mean, it's a really good article. What also you can do, if you go to Hugging Face, where you have all these models, so let's say, for example, we go for Mixtral or Mistral. Let's go for Mixtral. Okay, so I go to Hugging Face. So this is repository. And this is particularly, so if I go to Mixtral, so first of all, this is models. Under Transformer, there are like 200 different models. You see, and Llama here, like all the models are here, which Transformer Python module support. And here we will go for configuration of Mixtral. And yeah, and you will see definitions of all the parameters. And you will see how they initialized and how the model structured. And if you go to modeling Mixtral, this is actually the model itself. So here you will see all the layers, all the objects, like everything. So this is the actual model. So let me just scroll it down. So how many lines of code we have? About 1500 lines of code. This is the whole model. You can take an hour and look through the code, and well, that's what we're running. Okay, so Mixtral of experts. This is 8 experts in parallel. Each model is 7 billion parameters. And 8, you see, this is the only thing which is multiplied by 8 is this layers of experts in the second half of each layer of the model. So this is only these pieces. So actually, you don't take the whole model and multiply it by 8. There are only pieces. So the actual size of how many bytes, how many parameters is about 47 billion parameters for Mixtral. Okay, for every token at each layer, a router network selects 2 experts to process the current state and combine their outputs. Even though each token is only 2 experts, the selected experts can be different at each timestamp. As a result, each token has access to all 47 billion parameters, but only uses 13 billion active parameters during inference. Mixtral was trained with a context size of 32 kilotokens. What is context size? This is the maximum number of input tokens. This is 32,000. And it outperforms or matches Llama 270B, GPT 3.5, and so on. So this is a very powerful model, and it's completely open source. In particular, Mixtral vastly outperforms Llama 70B on mathematics, code generation, and multilingual benchmarks. Oh yeah, this is another thing. They trained it on European languages. Llama basically understands only English, but Mixtral understands multiple languages. We also provide model fine-tuned to follow instructions, which is called Mixtral 7B instruct. So this is the same model, but it's trained on a different set of data, on like question answer that surpasses GPT 3.5, Turbo, Claude, Gemini Pro, and Llama. Both the based and instruct models released under Apache license. Apache is very permissive. That means you can use it in business for your profit. Yeah, which is good. So here are some links, some articles. And next, a little bit more explanation of what mixture of experts is. Like historically, it all started in 1991, and over the years, people have done a lot of experimentations and analysis. One worth mentioning is a switch transformer developed by Google. They published it in 2022. It has more than 2,000 experts. Just think about it, 2,000 experts. And each expert is about it's close to 1 million parameters. So together it's about 1.6 trillion parameters. And if each parameter is 2 bytes, we're talking about more than 3 terabytes of data just to keep the model. Of course, Google have their TPUs, thousands of them to run this model, and they outsource it, open source it, but I don't know who can run it. Like, you need a really big system to run it. Okay, how an LLM generates output, inference. Well, I already told you that it does it in circle, generating one token at a time, right? But here, I just go step by step. So we have a sequence of tokens, we convert them into sequence of vectors. Then there is a step which I haven't covered yet, but we will cover it in more details, how we embed the positional information of each token into the embedding vector. It's done like in a tricky way with the sine and cosine functions. Then we have transformer layers. Each transformer layer consists of self-attention and feed-forward parts. Then at the end, we have output embedding vectors. We map them into vocabulary of tokens, and then we run it through softmax layer to kind of normalize and select the tokens with highest probability. And then we select the next token. And there are several strategies how you select the next token. We'll cover it later. And that's basically it. And then you go in circles. Okay, let's now go it a little bit deeper. So first of all, at the beginning, we take text and we convert it into tokens, tokenization, and then we create embedding vectors, right? Well, tokenization is convenient because when you have long words which may consist of pieces, small tokens, and as a result you have the whole vocabulary of tokens is about 30,000, whereas vocabulary of words is much bigger. It's easier to work with tokens, and everybody is doing it. Now, embeddings has a long history, embedding vectors. So what you do, you map each token to a vector. I want to cite this work which is called Word2Vec. It was done at Google in 2013, and key person is Thomas Mikolov. And the article is Efficient Estimation of Word Representations in Vector Space. So it's an archive, you of course can read it. And this is, this is absolutely classical work. So what have they done? They converted each word into a vector of the length 50 up to 100, right? Why they have done it? So the question is how you represent the meaning of the word. So let's say you have two words or two tokens, whatever, let's say two words, and they have the same meaning, they're synonyms, but they spelled completely differently. So can you find a representation using numbers, using vectors, so that synonyms will have similar vectors? And that's what they've done. And the solution was very simple, in fact. So they said, okay, first populate vector for each word with random numbers. Then if two words are synonyms, you can probably meet them in the same sentences. They're interchangeable. So they can be defined by their neighbors, by the words which coming before and after. So you can kind of calculate the average of their neighbors and add it to the vector in the middle, right? Tell me who your friends and I'll tell you who you are, right? So by using this approach, you can do it over and over again and eventually converge, and you have vectors representing words, and these vectors allow you to do some simple vector arithmetic, like for example woman and man and queen and king. So you can say like king minus queen, same as man minus woman, and it actually works. So it's very funny. So you can train it once and you can have a mapping from words to vectors or from tokens to vectors. And yeah, and you can do it, and you can just at the beginning of LLM you can just convert tokens into these embeddings using some standard predefined like matrix of this conversion. So the tokenizer used by Mistral is actually sentence piece byte pair encoding tokenizer. So here it is at GitHub. You see, this is open source tokenizer. But then embedding model, they actually created their own model. And another interesting thing that the length of those embedding vectors is about 4,000. So they're pretty long, much longer than what was used by Mikolov and his team. Okay, next, just step aside talking about embedding models in general. So what embedding models can do, like in this case, we convert just one token into long vector, but sometimes people do different thing. They take long text and convert it into short embedding vector, right? And when they do that, they need some sort of aggregation strategy to compress the long text into a short vector. And there are multiple strategies, including pooling, which is averaging, maybe attention mechanism, maybe fully connected layers. So let's say you have one layer with 10,000 nodes and next layer with 1,000 nodes, and they're all interconnected, and you train this network to convert 10,000 into 1,000, right? So it all works, but only so far. Actually, this post discusses that you cannot really compress too much because you're losing information, or you're mixing because if the text is long, it may contain multiple ideas and then you cannot decipher them, like separate them from each other. So truncation and chunking are still the best strategies for longer contexts when you create embedding from a piece of text. Okay, but this is a side step from talking about transformers. So next is how positional information is added into embeddings. And this is really tricky. So what's happening, just a second. What's going on? Oh, okay. Here's what's happening. When we took the tokens and we created the vectors, right? Now, tokens have positions. Let's say the 0, 1, 2, 3, and so on. Let's say we take the position, and the position may be odd or even, right? So now, so this is what we do for even, and this is what we do for odd, right? The position is 2i for even and 2i plus 1 for odd, right? And then for no, sorry, not the position, the index in the vector. So pos is the position, and 2i or 2i plus 1 is the index inside this vector. So we calculate this value as a sine or cosine using position divided by something. D is the dimension of the model. This is the length of this vector. Okay, and what you do, you add those numbers to corresponding values inside the vector. So it's really strange because you're mixing apples and oranges, right? You had some representation of the token, and then you mix into the same values, you mix this sine and cosine values. And that's how it works. Original article describes why they decided to do it. One of the reasons was they want to use periodic functions because they're interested in a relative distance between the words in the sentence. Also, this thing effectively has different sine and cosine frequencies. So it's kind of like Fourier transform. So it helps you to encode the distance more precisely. Anyway, this is how it's done. And this is well, actually, I really like this graph. It comes from this paper from Germany, and the authors, they created pretty good description of how things work, and they provide this graph and explanation. So I copied it, giving them reference, and want to explain what it is actually. So let's go step by step. Yeah, the things which circled with red, these are things which actually constitute the model. These are things which are remembered. Like when you have a model file, these matrices are stored there. And so we start with words, tokens, we convert them into vectors, we embed positional information into these vectors. So this is X, is this set of vectors. And then we multiply those vectors on this matrix, on this matrix, and on this matrix. And these matrices have the same shape, the same size. Like, for example, for Mistral, they have size of 4,000 by 4,000 approximately. And then you see this multiplication and this multiplication, then this is transposed and they multiply together. And my first question was, why the hell they do this? Why can't they combine these two matrices? And and I will explain why. And then they multiply these vectors again on this matrix, and then they combine it with this multiplication, and then they process it a little bit, and the result is called attention matrix. Right? So this is attention mechanism. Right? Then you multiply on yet another matrix, which is again trained during the training process, and you get the output matrix, which then you mix in again those vectors, residual connections, normalize, do feed-forward layer, which looks like this, and so on. So this is attention mechanism. People try to explain how it works and why this is called key matrix and this is called query matrix and why this is called value matrix and weight matrix. But so for you, just these are just matrices. This is the structure, and somehow it works. It's proven that it works. I also want to add something which is not on this diagram, which is at the very last, after you exit the very last layer, and you get this set of those vectors, there is another block which actually generates the next token, the next word. It's not on this diagram, but everything else is basically here. Okay. Next, I want to talk about multi-head attention. So this is one head. And in Mistral model, they have 32 heads. So you have 32 heads, and each one has all these matrices. So for example, now you have not one key matrix, but 32 of them, 32 of this, 32, 32. So it's a lot of matrices. And you see on this picture, query key value, query key value. So you have multiple heads, they're called heads. And they trained independently, separately. So these matrices are not the same. And then you combine them, and it's very interesting how combination is done. So when you exit here, you get each head produces a set of vectors, right? And then you concatenate them, you get a very, very, very long vector. And then you use a small network to return to the original embedding dimension. Okay, in Mistral model, there is a strange optimization. They actually take these 32 attention heads, split them into 8 groups. So each group has 4 heads. And then key value matrices, which is this matrix and this matrix, are actually shared inside this group, inside each group. Okay, I don't know why they decided to optimize for key and value, but whatever, and this works. So next, steps of attention mechanism. So we'll just go through this diagram step by step. So first we multiply input embeddings by Q, key, and V matrices. So we do this multiplication, and this multiplication, right? Then we multiplied Q by K transpose to get a score for each query. So this is, we're multiplying this by this, and we get this. Okay? Divide by square root of dimensionality for normalization. Apply softmax to the scores to convert them to attention weights. And we calculate the softmax. Multiply by V. So now we're multiplying by V. This is V. And we get the attention output. Right? The attention becomes the new representation for each query token. Optional final linear transformation can be applied back to the model dimensionality. Okay, the sizes of the attention mechanism matrices are the same. Normally they would depend on the length of the input, but Mistral and Mixtral, they use window attention, which we will describe on the next. And this window, sliding window, is 4K. So the length of these vectors is 4K, and the window is 4K. So these matrices then, all these matrices are 4 by 4. I mean 4000 by 4000. Okay. If you look in the actual Python code, you will see function calls which receive batch size, number of heads, sequence length, and head dimension. But anyway. Now, about sliding window attention. So Mistral 7B has a maximum input sequence of 32,000. So it's approximately 50 pages. It's a long sentence. Each layer processes these long sentences using sliding window attention, so of 4K length. It does it in overlapping chunks of 4,000 tokens, approximately 6 pages. The window is sliding across the entire input sequence. Okay, so first we set initial window, which is the first 4000 vectors. Then we're sliding forward by 256 vectors, and we continue it iteratively until we finish. So instead of having huge attention matrix of 30,000 by 30,000, we use smaller pieces. So this is the way to optimize to decrease the amount of memory required for the model. Okay, why can't we combine the query and key matrices into one? Yeah, it's the question, why can't we simplify a large language model into just one node, right? It actually works because there are multiple pieces, and you need to split them into multiple pieces to get this richness of functionality, right? The power of Gen AI systems grows with increasing the number of parameters. A good model like Mistral has billions of parameters. They are structured into 32 layers, each layer having 32 attention heads and feed-forward layer, and each attention head has multiple matrices and normalization layers. Combining matrices may appear attractive, but doing so actually reduces representation power, limits comparisons, eliminates potential design innovations, and so on. Extra matrices and extra nonlinearity provided by splitting the embedding across multiple matrices contributes significantly to success of attention-based models. And here I list some benefits specifically for having a query and key and value matrices separate. Okay. The end part of the transformer. So after we went through all these multiple layers, and we get to this exit part where we need to generate the next token and add it to the beginning, right? So what's happening? So suppose we have a large language model and input has only 5 tokens, right? We convert them into embedding vectors of size D. For Mistral, D is about 4000, right? So this is the size of the vectors, dimensionality of the vectors. This embedding pass through multiple transformer layers. The output of the final transformer layer consists also of 5 updated vectors, each still having size D, right? Then we multiply the output by an unembedding matrix. So the unembedding matrix is actually a variation of embedding matrix. It's not trained separately, it's derived from embedding matrix. And it's usually called W unembedding, like this. And when you go from your vectors through this matrix, you get another matrix which have a size 5 times V. V is the length of the vocabulary of tokens. So if this vocabulary has 30 or 32,000 tokens, so this will be this matrix. It's a two-dimensional matrix. And then we apply softmax function to each of the 5 rows. So at the end, we'll still have the same shape of the matrix, but the values will now be probabilities. So we'll go from logit to actual probabilities. Finally, we'll look at those probabilities, and in the last row, we find the one with the largest probability, and this will be the next token. So each position in this row corresponds to a token, and the one with the highest value will just take it, and this is simple tactics. And another thing people sometimes do, they select not the top one but several on the top, and then they randomly select one, which is called sampling. And yet another thing which is more advanced, but this is actually what's used in Mistral, it's called beam search. We keep track of multiple potential sequences called beams and expand them at each step, eventually selecting the sequence with the highest overall probability. So this is more complex, but definitely will produce cleaner output. Okay, so how Mixtral was trained and run? In the Mixtral paper, they say, we thank the CoreWeave and Scaleway teams for technical support as we trained our models. We are grateful to NVIDIA for supporting and integrating TensorRT-LLM and Triton and working alongside us to make Sparse mixture of experts compatible with TensorRT-LLM. So what is it? So TensorRT-LLM, it's on GitHub. So you can like look at it. It's from NVIDIA, and we're also where is it? I wanted to find Triton, but then this is this one, Triton Inference Server. So this is this one. Okay. So let me close it. So what's going on? This is an engine to run large language models. It's very fast. It's very optimized. It has a Python API similar to PyTorch. It allows you to define LLMs and builds engines, which then you can use for inference. So it's a highly optimized environment to run the models. And they support different formats. They support TensorFlow, which, well, nobody is interested anymore, and support the Open Neural Network Exchange format, and support PyTorch TorchScript format, .pt. So they're very flexible, and that's what Mistral team was using. So is having more experts better? Well, is 8 is optimal, or maybe they need 16? Well, Google went to 2,000 experts. So what's happening, more experts, you need more compute. It may become more expensive, and for many tasks, it may be overkill. For smaller data sets or simpler problems, adding more experts may result in redundancy, overfitting, reduced generalization, and of course it's more expensive, so maybe it's not good. A more complicated gating network may also be needed when increasing the number of experts, so it also can be more difficult. Okay, this is a good article, The Rise of Sparse Mixtures of Experts, Switch Transformers. And here I provide some information about open models, or maybe not open, but where information is known. So you see from 2020 to 2023, so there are different models. They have different number of parameters. They have different number of layers. Llama and Mistral and Mixtral have 32, but there are some others, like for example, Palm from Google, it's huge. It has more than 100. GPT-3 has 96, about 100. Embedding dimension, this is in the feed-forward layer in like each layer. So this is the maximum like width. You see it's, well, ballpark is 10, right? A little bit less, a little bit more. And the number of heads. For Llama and Mixtral, there are 32 heads inside attention. Okay, this is, I think, the end about Transformer. And now I just want to cover some news, just a little bit. So first is this publication in Nature by Google DeepMind. They created a model called AlphaGeometry, which solves geometrical problems. And you see here the medalists, Olympiad gold medalist standard for solving geometry. So you see this is bronze medalist, this is silver medalist, this is gold. And the green is AlphaGeometry. And it is very close to being gold medalist. And you see, this is the previous state of the art, so it's a huge progress. They created their own language, neurosymbolic system to solve these problems. It's extremely impressive. Another piece of news, this company called AlphaCodium. It is from Tel Aviv, from Israel. And you see these young people. And what they did, they made a system specifically designed for coding. And it is iterative, it is test-based, it is multi-stage, and it provides very good results. So these are some links. It's on GitHub, it's open source. So that's probably maybe the way to go. Another big thing is this Mark Zuckerberg's announcements. So he released a 2-minute video, which everybody is talking about. Basically, he's saying that they're really focused on AI. He was talking about 350,000 NVIDIA Hopper 100, H100, and other hardware, which is equivalent total to 600,000 H100s. I tried to estimate the cost of this. The one H100 is about $32,000. And if you multiply 600,000 by this, you get about 20 billion. So, and this is just the price of GPUs, and you need to probably double it to get the price of servers, and then you need to, I don't know, maybe add another 20 billion for the price of construction of those data centers and so on. So this is a huge investment, maybe let's say about $50 billion. Meta really has become an AI company, and they are training Llama 3. This was his big announcement, that they are training next generation, and it will be open source. And yeah, this is very bright future he's describing. Okay, some other news. SDXL. So Stability AI has a model for image generation called SD and XL, SDXL. And my son was playing with it, and there are multiple GUIs or like systems which you can use to run it on your own computer, whether it's Linux or Windows or Mac. And one is ComfyUI, which people seem to like. And here are some links which you can follow. This is a good link to calculate OpenAI ChatGPT pricing. I actually don't advise to use OpenAI because there are other models which are as good or better and much cheaper. New Samsung Galaxy S24 is released, and it has a lot of AI features. Some of these features, like for example, circle to search or live translation, where you can talk to somebody and in real time the person will hear in different language and vice versa. Similar features were actually released by Google and available on their latest Pixel 8 and also Circle to Search, but it looks like Samsung has its own proprietary versions of the same features. They also have nightography zoom, which is also AI based. So the new Samsung, it's all about AI. And Microsoft launches Copilot Pro, $20 per month, to have access to the latest Copilot features. Volkswagen and Mercedes-Benz demonstrated dashboard LLM-based voice assistants. Oh, this is interesting. Taiwanese startup New Chips displayed add-in board that enables desktop computers to run 7B LLMs at only 55 watts. Well, this is really impressive, right? So it's not a GPU. It is a specialized board which consumes very little energy and can run good model like Mistral, for example, in your desktop. They're not producing them yet. They're supposed to be maybe in half a year from now. Now, this is actually a screenshot from my browser. And you see I have a folder called S for search. And here I have Perplexity, Bard, Hugging Chat, Llama 2, Claude 2, Bing Chat, and GPT-4. I really like Hugging Chat because it runs Mixtral, and in my experience, it's really good. It's better than GPT-4, like in my experience, for the questions I'm asking. Maybe because it was trained later and GPT-4 is still kind of obsolete, doesn't have latest information. I don't know. This mega dolphin. Okay, what this person did, he took two Llama 70 billion parameters and interleaved them together into one model, and it's called Mega Dolphin because the original one was fine-tuned on Dolphin dataset to become uncensored, and apparently the new model is better. It is uncensored, and it also is tuned for conversation and empathy. So it's a really interesting development. Meta is very proudly says that using AI improves return on advertising investment. Here is the book, a 200-page book for free on vector retrieval. Now, today I looked at how to run Mixtral cheaper, and one thing I found called Monster API. And so monsterapi.ai is a website, and they have option where you can deploy any model you want. Like for example, you want to deploy Mixtral, you can do it. It's very, very affordable. The author of the tweet, this original tweet, claims that he used to spend $100 a month on OpenAI, and after he switched to this, his expense is less than $1. So it's 100 times cheaper. self-rewarding language models. I mean, this is really huge. So what they are doing here, the model trains itself iteratively. So you see iteration 1, iteration 2, iteration 3, so it's a 20 and a half, which is around Mistral medium or GPT-4 level on the comparative leaderboard for this particular test. So this is absolutely amazing result, that the model can self-improve. So this is the link to the article, and it was just published. I think it'll be a lot of following for this article. Next, I mean, this is too much for today, but somebody asked me about running AI on clouds, and there are tools, like for example, everybody asks about Amazon Bedrock, or on Azure, there is a lot of, well, of course, Azure OpenAI, and there are many other tools, and so it's on Google. They're very close to each other, very comparable. I usually don't like to use the tools they provide because you end up paying 10 times more than you could pay if you just install stuff on a Linux box. But sometimes there are benefits because you can do things very fast, and they have things already pre-configured and ready to use. Big companies love it. I don't. Anyway, Hugging Face leaderboard. So what's interesting here is this particular model, which is Mistral based, I think, but it is experimental. It uses two models of 7 billion parameters. So it's a mixture of experts, but only two models. But somehow it achieved great positioning in this leaderboard. I don't know. Next is the usual crowdsource arena. Well, things haven't changed much. On top, we still have GPT-4. This is Mistral Medium, which is not open source. It's available by API. But then you see the green ones. These are all open source. So here you have Mixtral, which we described today. And this is Yi model from China, from 01.ai. This is Llama-based model, and so on. Okay, this is yet another leaderboard. This is AI tools as usual. I added text again, web UI. This is open source. You can find it on GitHub, which is a good way to run models on your local computer. And that's it for today.